Hey guys, so today we're going to be talking about inequalities and how to graph them. So just like the equal sign, inequalities are just a series of truths. Generally, these are used to represent relationships between variables, and let's just say, take the equal sign for example. That represents a equality relationship. The left is equal to the right. Inequalities represent a case where one side is bigger than the other side. So generally, this sign is the less than sign. And that means that the left side is always less than the right side. Likewise, this is the greater than sign. It means that the left side is bigger than the right side. You can just remember these as Pac-Man always eats the bigger number. So instead of saying, if you're comparing 3 and 1, right? Bigger number's 3, your inequality sign is going to be going towards the 3. It's a very rudimentary way to do it, but I find that it works for me sometimes. So when there's a straight line underneath these, that gives us new operations, but they're basically the same thing. This just means that equal to or less than. So in this case, this sign doesn't allow for the two sides to be equal. This sign does. Equal to. And this one's greater than or equal to. So let's just say we have an inequality, right? This is going to be one with no line. It's going to be x is less than 3, and the possible values of x range from anything from like x equals 0, x equals 1, these work, x equals 2.999, that works. The only thing that does not work is x equals 3, because the inequality says that x is always less than 3, so they can never be equal. However, if you have a less than or equal to sign, x0 still works, x is 1 still works because 1 is less than 3, x equals 2.99 also works, still less than 3. But since this sign is a less than or equal to sign, x equals 3 also works because x is allowed to be equal to 3 by this sign. Now let's go over operating on inequalities. So you would operate on an inequality like you would operate on an equal sign in most cases. When you add or subtract from an inequality, you do it to both sides. So in this case, since x is less than 3, x plus 1 has to be less than 4. What we've done is we've added 1 to both sides, and this makes logical sense, right? Because if x is less than 3, that means like, it could be like 2.9999999. If you're adding 1, you're still getting 3.99999 something something, less than 4. That's still true, right? You're adding the exact same thing to both sides. So if one small number smaller than another number, if you add the same thing to both numbers, you know, the relationship is not going to change. The number size will, but one number will always be smaller than the other. Similarly, when you multiply or divide an inequality, you also must do it to both sides. So let's just say I wanted to multiply both sides by 3. So I get 3x is less than 9. Again, let's just say x is 2.9 for simplicity this time. And this statement is true. When we multiply it by 3, we're doing the exact same thing to both sides, right? So the limit of what 3x can be is 9. But we know that x is always going to be less than 3. So 3 times x, which is a number that's less than 3, is always going to be less than 9, which is 3 times x. So in this case, pretending that x is 2.9, you know, small number still smaller than 3, we multiply 3 to both sides, and then we end up with x is equal to 8.7. Sorry, 3x is equal to 8.7, which is then, again, still smaller than 9. So there is a exception to this. When you want to multiply or divide by a negative number, you must also flip the direction of the inequality. If you play around with it for a little bit, you can see that for all values that satisfy the first equation, the second is only true with a flipped sign. And that's because we multiply both sides by -1. It's basically like we reversed the direction of the inequality. So, sorry, this should actually be like that. Multiply both sides by -1, and now we flip the signs. This is our new inequality. So, now let's talk about graphing inequalities, which is the primary focus in grade 11. So we're going to take the inequality y is less than x plus 3 as an example. First, to graph it, obviously we need to draw the Cartesian graph. And we want to see what we are comparing y to. So the best thing to do is to plot x plus 3 on the graph. The inequality is either going to be greater, less, or equal to it. Regardless, we want to see what we're working with just so that we can use it as a reference. So, because we know that at any x value, let's say x equals 1, its corresponding y level is going to be less than x plus 3, which is displayed on the graph, given that this point is 1 and 4. For reference, this is the graph of y equals x plus 3. So if you would like to verify any of the points yourself, please do. Anyway, yeah, we know that at x equals 1, anything that is less than 4 makes this inequality valid. So now I'm going to say that at x equals 2, we have 0.1 and 0.2. Let's compare them. 0.1 is less than x plus 3, which is here. I'm going to call this point P. Since it's less than x plus 3, it is a valid solution to the inequality. 0.2, however, is above point P, and therefore the y value is greater than x plus 3. Therefore, this is not a valid solution to the inequality. So if you wanted to check every single x value and every single possible point, you would basically have the entirety of the underside of this graph covered. And notice how in the first quadrant, there's almost like as if an area is created underneath the graph. Anywhere in this area, right? At any point x, the inequality will be valid. And I do realize that I am limiting this to quadrant 1 right now. Some questions will ask you to go into quadrants 2, 3, 4, but for the sake of simplicity, we are keeping the explanation in quadrant 1. So this area is exactly what we're looking for. It's a portion of the graph where any point, point x, y, will be a valid solution to the given inequality. Will you ever need this in the future? Probably. Up to calculus 2. Yeah, you will. You'll encounter these a lot. Now, okay. Let's graph some systems of equations inequalities this time. Which is, it's a little bit tougher, but it's the same concept. You're looking for areas where solutions to inequalities are valid. So sometimes you'll be given a system of equations, and you're going to be asked to solve for inequalities with multiple parameters. So that means y is less than a, but it's no more than b. So y is between b and a. So an example would be y is less than negative x plus 2, but y is greater than 3x plus 1. So, how would we approach this? The way we go about this is pretty simple. We're going to first plot both inequalities on the graph and see what we're working with. So, the graph of negative x plus 2 roughly looks something like this. And the graph of positive 3x plus 1 roughly looks something like this. I'm not putting units on here because the units don't really matter that much. But, sorry. Yeah, the units don't really matter that much because we're only looking for areas and conceptual ideas, not really solving for anything right now. So what we're looking for is the region that satisfies both criteria simultaneously. Let's start by shading in the area that's possible if we were only to consider one inequality, which is y is greater than 3x plus 1. So 3x plus 1 is this line right here. I'm going to hide, I'm actually just going to draw this one in red. I'm going to put a box next to it just so that everybody knows this is y equals 3x plus 1. So we're going to shade in every region that satisfies this criteria. So every y value above this satisfies the inequality y is greater than 3x plus 1. Of course, this probably makes sense by now. Now, after we've done this, we can introduce the second limitation or inequality. In this case, y is less than negative x plus 2. So the white line we have here, we first drew, is the line negative x plus 2. This limits the shaded area instantly to only under the area under the line of negative x plus 2 and above the line 3x plus 1. So that means that all of the shaded area up here is now an invalid solution because it works for one function, but it does not satisfy the conditions of the other. And we're looking for the area that satisfies both. So what we end up with is this area right here. Above the red graph, below the white graph. Oh my god. Okay. Nice. Yeah, that area right there, that satisfies both inequality equations. Any other regions violate either one or both of the inequalities given in the system of equations. That's the basic concept. I would say this one is fairly intuitive, but it does require a bit of practice to get, and we are going to go do some practice problems now.